some time. Okay. Triaxial testing, and this is where spend some time, because when I go to block 4, which or the repeated loading, we're going to rely on this quite a bit. So I want to make sure that we're all on the same page. So we're talking about cylindrical triaxial, and you know that why it is cylinder, we talked about it. So we have a chamber. Inside the chamber we have some kind of a confining fluid or what, right? You've used that and stuff, and when you apply some kind of a confining pressure to this chamber, it's Pascal's law, it is normal in all directions, it is hydrostatic, it is equal in all directions and stuff like that. So what happens is it's something like a sigma c is the confining pressure that you apply. So if you, at the very initial stages, you have all of these are sigma c, right? And then you have a mechanically applied deviator stress. Those of you, okay, let's do a quick show of hands here, and please be very honest with me. How many of you are being exposed to triaxial testing for the very first time? 1, 2. Have you seen triaxial before? 3, 4. Okay, 5. Okay. So triaxial testing is done inside a chamber, and then you fill a sample. So it can be it is usually a cylindrical sample. It can be, if you're working with the soils, fine soils, you can have diameters in the range of like 2.8 inches, 4 inches, 6 inches. This is inches diameter, up to 12 inches is what I have tested in my life. So it's 12 by 24, which is like 300 millimeter diameter, 600 millimeter samples. So this is railroad ballast and stuff like that. So you're pressurizing the system, and you're applying what is known as confining pressure, and then you apply what is known as the mechanically induced deviator stress, and we call it deviator because that is what is the deviation from its standard state. When the truck goes, when a train goes, when an aircraft goes, that's where the load is, right? So basically in the vertical direction, sigma v, then you call it sigma c plus sigma d, and sigma h. There is a reason I write it as h. I'll tell you. You'll realize when we go into resilient modulus in next couple of days, it stays as sigma c, right? And what I was saying is, because in the vertical, and we agreed that because there is no shear here, these are all principal stresses. So this becomes your major principal stress, which is sigma 1. This becomes your minor principal stress, which becomes sigma 3. And in this case, because we're talking about a cylindrical specimen, sigma 2 and sigma 3 are the same, is the same, right? So now what you can do is you are going to apply the deviator stress at a given rate, and then you are going to punch, or not punch, you are going to deform the induce axial deformation in the specimen, and then at one point you're going to have some kind of a shear failure, right? Because soils, aggregates, they always fail in shear. Even if you induce them, again, master students, PhD students and stuff, even if you induce compressive loading into these things, you are actually failing in shear. So that is the reason you measure shear strength and stuff, right? So imagine this is, let's go into a more circle kind of a frame, sigma versus tau, right? At the very initial stage, I have not applied any sigma d. I haven't applied any sigma d. How does my Mohr circle look? A point, right? Because it's a point. It's just a point. It's hydrostatic. It's the same stress under ice, exact same. So this is what your sigma c is, and then you increase a little bit, 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 increase a little bit, increase a little bit. At one point, it's going to touch what is known as the failure envelope, right? What is a failure envelope? Why do we call it an envelope? Because it envelopes, it contains everything underneath. There is nothing above it. There is a stress state here cannot exist, right? It's a failure envelope, right? What is the most common one that we use? What is this called? What kind of failure envelope? Mohr Coulomb, right? C plus sigma tangent of phi, right? C is the cohesion. I like to call it apparent cohesion because not all materials have cohesion, right? But so that's the reason there is a linear. So a little bit of additional information for you. The Mohr Coulomb envelope is actually non-linear in nature, but you are actually doing a linear interpretation, and that is the reason you always, a lot of times you have the C or an interpretation C. So you just have to remember that it's not truly linear, it's a non-linear envelope. Okay. Now this is sigma 3, this is sigma 1, that's the major principal stress, minor stress and stuff. At the second stage, when I do another test, what will happen? This is, let's just say this is 5 psi. Now I'm going to increase the confining pressure to 10 psi. Start this test at 10 here. So what will happen? The circles will get bigger, right? Because as sigma increases, your tau also increases. That's frictional behavior, right? That's frictional behavior. What if it is no friction? What if phi is equal to 0? How will the envelope look? This, right? When do you see this? Okay, clay, pure clays, yes. You said something. Yes, when you have 100% saturation, then what you are trying to still work on the total stress and stuff. What will happen is all the stresses are actually taken by water. So when you are applying additional if you do it undrained, so when you apply additional loading, all of the loading is taken by water, so you're not gaining any strength. That's what happened, right? Though consolidated, undrained and stuff like that. Those, so you'll see those behaviors sometimes. So anyway, so now it's this get bigger. You have your the failure plane. You usually draw 3 and then draw a tangent. That's what we're going to do on in the tutorial today. You're going to see how this is done, right? And how you can determine this, how the data looks. That's what I have for you today. But the bottom line is you are going to use a Mohr Coulomb failure envelope, which is going to give you so just do this, maybe like one circle here, one circle here, one circle here, and that's what a typical triaxial testing does, right? When you go into geotech, pure geotech, you can go into all the different forms like unconsolidated, undrained, unconsolidated, consolidated, undrained, consolidated, drained, unconfined compression and stuff like that. One more thing that is very relevant to us in pavement side of things is unconfined compressive strength, right? What is that? What does that mean? How does the Mohr circle look when I do a unconfined compressive strength? Sigma 3 is 0, right? Sigma 3 is 0. So this is called unconfined compressive strength. This is basically your, this is the compressive, no wait, this is known as the compressive, right? And then you have the double, the radius is basically half of that and stuff like that. That's how it works, right? So why did I go through all of this? Is we are going to talk about both strength and modulus using triaxial testing. Okay. Now, is everybody familiar with what is a strain controlled test versus what is a stress controlled test? Yes, I see some yes, some no's. Okay. So let's do a very quick review on that. How do you, let's think about a machine that you are running now, and you are going to say that I want you to apply 5 Newton of force on this table. How does the machine know that? How does it do? Have you ever thought about it? Yeah, but what is calibration? I mean, what's the science behind it? In crude language. I don't need exact science. Crude language. What is happening in there? Say again? No. That's the. I mean, we're not doing any free fall or anything. I have an actuator. I'm trying to push a piston. I'm trying to push. Yes, measuring the resistance, but how is the 5 set? No, why? Why is 5 related? That's a very good point. We'll get to that when we go into modulus and stiffness, but that's not necessarily true. So what he just said, it's very important, is that he's saying that I am applying 5. If I am stable here, then I am 5. I can apply. If not, then I cannot apply the force, right? Can you push my hand? Apply some force. Push. Push. How much force are you applying? Now push, right? So what is that? This is sample. This is my sample, right? So if my sample is going to resist, then only my load is going to be valid. Otherwise, load is 0 if the sample is moving. But that's we still haven't gone there. That's an important point. We'll get to that in a second, in maybe tomorrow or something. But how is a machine applying the load? There's something called a feedback loop, right? It's a feedback loop, feedback system. Imagine you are saying that, imagine you are hanging a photo frame in your wall, and you have your sibling or whatever, your friend or whoever standing behind, saying that, okay, let me know when it is straight. First they say, go a little bit right, and then say, no, too much right, go back, then go back left, and stuff like that, right? That's feedback for you. You have a sensor in your loading system. When you are applying a load control test, you have what is known as a load cell here, right? The load cell continuously keeps measuring the load that it is feeling, and then it keeps sending back to your computer saying that this is what I am feeling. So when I am applying, my target stress is, say, when we go into resilient modulus, you will see this. When my target stress is 10 psi, the load cell keeps measuring it, or the pressure cell keeps measuring it, saying that no, I'm at 3, go up. So then you go up to 7, like no, still keep going up. Then you go to 13, it's like no, too much, go back, 10. This keeps happening at 1,000 times per second and stuff, at a very, very fast rate, right? So that's called feedback, Okay, and the thing that governs that is something called PID, proportional inverse and derivative gain. We are not going to go into that. That's an equipment stuff, design stuff, right? So a stress controlled test in the real world honestly does not exist, because a machine only has control over what? The deformation. Machine does not control the force. What is the force dependent on? Your sample. I just showed you when he was trying to push my hand. I moved, so the thing was moving, right? So the machine actually is just saying, even if it is a stress control test, it is saying that I'm going to apply 0.1 millimeter of deformation. And let's see how much force I'm feeling. If it is not 100, if it is 2000, it's like, oh wow, this is way too much. I need to go 1/10 of that and stuff. So a machine is nothing, it doesn't know anything other than applying deformation, right? But the test can be, a triaxial test is deformation controlled or strain controlled. You say that I'm going to apply 1% strain per minute, and then I will just keep pushing this sample. Whereas when we go into modulus testing, you will see that I'm going to apply a 10 psi load pulse every 0.1 seconds and stuff. So because it's all triaxial, I wanted to give you this background on what is stress control versus what is strain control. So just remember that. What is it are you asking the system to do, right? In triaxial testing, you are or shear strength testing, it's called monotonic triaxial testing, because monotonic means you are just pushing it at one given rate. Okay. Other than that, resilient modulus and stuff, when we get into that, it's called repeated triaxial testing, because you're going to pulse it. That makes sense? There is another term a lot of times people use. They call it dynamic triaxial testing. Okay? That actually is probably the last thing we're going to say before we break for a little tea break. I'm going to highlight one little thing to you folks, and again, this is all going to build up on each other, so it's going to be relevant for you. When people say something like, I am determining dynamic properties using resilient modulus testing and stuff, right? Let's go back to our basic equation. What is F? Who can tell me K times X plus, tell me the other two terms. C X dot plus right, spring constant, the deformation term, the damping factor multiplied the velocity, the rate dependent term, and then the inertia term, right? This is a truly dynamic system. If you are analyzing a test data in the real dynamic thing, then you have to consider the inertia effects, you have to consider damping effects. In resilient modulus testing, whenever we go into that, you will see we are kind of still simplifying it only to the first term. It is a repeated loading test, but we are not doing a true dynamic characterization. So it's not a dynamic property. Modulus testing is not dynamic. Okay, because you are not considering the effects of damping, rate dependency, the inertia, and stuff like that. So triaxial testing, what you from here saw is you can use it for shear strength, you can use it for modulus, and we can also use it on permanent deformation behavior. Let's take 2 more minutes to take care of that. Epsilon sigma, right? Static monotonic triaxial testing. Shear strength, how does it look? something like that, right? You have seen this many times, right? How would a repeated load testing look? You are applying something and then you are removing that. How would that look? You go up and then you come back. Where do you go back? To 0? Why not? It's going to have some plastic deformation, right? Next cycle, come back, come, do many cycles. At one point, you go into what is known as a hysteretic behavior. There is no further permanent deformation accumulation. That elastic stage is what we are going to talk about, is a resilient modulus and resilient stage. So is resilient modulus an elastic modulus? Yes, but after certain amount of plastic deformation has happened, and also it is something called a secant modulus, not an elastic modulus. We'll get into that. So why I showed you this is all this behavior from now on pretty much until the next 1.5 days and stuff, it's all going to be based on triaxial testing and triaxial behavior. Good? All right, take a break, 15-minute break, and then we'll come back. All right, okay, let's get started. Still have a lot to cover. So we are in triaxial testing still, just basic components here. The whole system is in a chamber, and that's what applies the pressures. The loading can be either pneumatic or servo hydraulic. Very recently, there is another loading system that's called electric based systems that I don't know that much about, but I have seen those. And we have the feedback control, and we are going to simulate in situ stress conditions on soil elements and stuff. So couple of questions for you to remember or pay attention to is, we said that we also do what is known as unconfined compressive strength test for subgrade, pavement subgrades, right? And unconfined compressive strength is when there is no confinement. But if you are under inside a layer, right, like let's just say this is a geotechnical engineering concept and stuff, and you're talking about a soil element here, the confining stress is because of the surcharge, right, the upper load. And what is that? You geotech folks, do you remember sigma h prime is equal to what? How do you go to from vertical to horizontal? K naught, right? Coefficient of coefficient of lateral earth pressure. So you do that, right? So the question is, why is unconfined compressive strength test still representative of what you are trying to do? And the best way to illustrate that is actually is there a wet like just a way to clean this or something? Otherwise it's just very difficult to see. Let us take a very simple pavement system, and you all will help me calculate some stresses. Okay, I'm going to put like a 4-inch, and my apologies for US units, because that's how I teach, and it's much easier for me to convert numbers in my mind. And then this is hot mix asphalt, 4-inch, this is aggregate base, 12 inches, and we're going to put a subgrade here. Okay, and we are going to calculate, is unconfined compressive strength test representative of us trying to characterize this subgrade. Okay, so let's just take, so the gamma for HMA is typically 150 PCF. PCF stands for pounds per cubic feet. Okay, and for base I'm going to make it something like 100 and let's do 12 inches. Let's just make it say 135 PCF. A well compacted aggregate base will do that, right? So let's do this quickly, folks. Total stress, we're going to ignore pore water pressure. So total stress is equal to effective stress essentially in this case, right? So total stress, vertical stress on top here. Spray kar do. Nale gote kaam kore chhadi ki poda. Manjire manjire use karibi nahole hote barambar nahole asubidha hoche. सब मिटा दिया. God. Sure, thanks. Okay, so 4-inch, 12-inch subgrade, we said 150 PCF, 135 PCF, and HMA and base, right? So let's do this. So sigma is equal to summation of gamma times H. I'm assuming everybody knows this already, right? Basic stuff. So 4 inches is what? This is PCF, right? So 4 over 12 multiplied by 150, right? Plus 12 over 12 multiplied by 135. So this is what? 3. So this is 50. This is 185. What? PSF, right? Pounds per square foot. We're going to make it into pounds per square inch. What do you divide by? Square of 144. So 185 divided by 144. Give me the number. .28 psi is the vertical stress on top of the subgrade because of the surcharge, right? What is a typical K0 value? Give me a typical K0. 0.33, 1 over 3. Very good number, right? Sigma H prime. By the way, I should not do it by sigma because it's kind of wrong because it's effective stress, but I'm ignoring pore water pressure. So sigma H prime is 1.28, 0.33 is equal to basically you're dividing by 3, so it's about 0.42 something, right? 0.42 psi is the horizontal confining pressure that this soil is experiencing because of its surcharge. Don't you think it's reasonable to just ignore it? Right? So that is the reason your soil is under so little confining pressure underneath the surcharge of a pavement. That's the reason you are kind of running an unconfined compressive strength is representative, because it's very low confining, right? So whatever you are feeling is based on the deviator stress. That makes sense? So shear strength, tau max. Sorry for the font, it's a little Mac versus Windows problem we always have. And this I have already shown you about sigma C, and sigma vertical is sigma C plus sigma D, and then you have a load distribution and stuff like that, right? That's should be straightforward. Again the same thing, but the shear plane you have a 45 over phi over 2, that's the inclination, and then that's where the failure occurs. Again typical geotech stuff. you have multiple tests you are running, you actually get different curves, and then you are going to try to quantify as the confining stress increases, but one is unconfined versus that confining. The way I teach it in my undergrad classes, you all are above that, but the way I teach it is, you imagine a bunch of marbles and then take a this is interesting. How did I do that? This even requires talent for me to do. How did I manage to do that? Okay, I'll try to write with this. We'll see. All right. You imagine a bunch of marbles. You take a, do you know what a saran wrap is? Like a sandwich wrap, like the clear wraps that you wrap food in, right? Take one layer of wrap around that marbles, and then you try to put some weight on it. After some weight, it's going to collapse. Now take an entire roll of that wrap and then wrap it around. Then you're going to be able to stand on it. That's confining for aggregates and stuff. That is what it does. Once it is held together, because the particles don't crush, you actually have immense amount of strength, right? So that is the reason confining will increase your shear strength a lot of times, as long as it is being translated into interparticle contact. If it is saturated, if it is undrained condition, if water is taking all the load, soil does not care, right? That's what happens. You saw this. We're going to do this in the tutorial today. Okay, this is sigma versus tau, right? This is how we plot or more circle, and then you draw a tangent. A little step back, you have also seen probably in your life what is a direct shear test, right? Right? What is a direct shear test? It's basically some kind of a block kind of thing. It's a square thing. You are shearing it on top of each other. What's the primary disadvantage of a direct shear test? Predefined failure plane. When is a direct shear test very useful? Sand, yeah, okay, but let's talk about even clay soils and stuff. What situation you can really easily simulate using a direct shear test? When you are analyzing, doing a forensic investigation of a slope failure or something, you can actually collect samples there, because it does already have a predefined failure plane. You can actually test the strength along that, right? So it's very straightforward. But why I am trying to ask you that is because your shear strength tests or direct shear, you have sigma and you have tau, and you get the points directly, right? You know that. You join that, that's your C versus P, C P. Whereas for triaxial, you have to draw more circles and you have to draw the tangent and stuff, and then you go. The point is, when you draw sigma 3 and sigma 1, so every triaxial test has a combination of a sigma 3 and a sigma 1, right? I actually try to call it not really sigma 1. Sometimes I actually call it sigma 1f, because it is touching the failure plane. So I call it sigma 1 at failure, not just any random sigma 1, because this is also a sigma 3 over sigma 1, right? It's not a failure condition. It's not touching you. It's not defining the boundary and stuff. So what you can do, I should have this. I don't know why I'm walking. What you can do is, this is actually what you will utilize in the tutorial today as well. If you just plot sigma 3 versus sigma 1 at failure for each test, and then you fit a straight line with that of the form of a plus b sigma 3, which is basically y equal to mx plus c or mx plus b, whatever. I think, do we still learn in this country mx plus c? Because in America it is mx plus b. So I have to change how I teach there. So I learned it mx plus c, and when I started like, where did c come from? I was like, okay, it's mx plus b. But sigma 1 is equal to a1 a plus b sigma 3. So this a and b are not the same as tau is equal to c plus sigma tan phi, right? And this is sigma. So this is actually some work that was done long back, and I have honestly not been able to track the source. I think it's from Purdue University, but they actually did this, and they were able to say that for any triaxial test, if you plot sigma 3 and sigma 1 and plot this kind of a line, then your relationship is cohesion is a over 2 square root of b, and sine of phi is b minus 1 over b plus 1. It actually works out like that, and when we analyze this afternoon, you will see you can actually do that and to give you the failure plane. It's very simple. It actually works like magic. Okay, so you can actually do this plot and stuff, and then this is effect of maximum grain size on shear strength. When you have Dmax increases, again remember we are all talking about interparticle contacts here, how that gives you strength and stuff. So bigger contacts gives you bigger shear strength. This is your unconfined compressive strength. I've shown you this. Of course, you cannot run this on sand or anything because there is no unconfined strength, but you can do it on stabilized soils, clays and stuff like that. You can do that. This is just some examples on how moisture content and dry density actually affect that. So moisture content is 23%, 26%, 28.5%, 30.5%. Your biggest enemy for soils is water. Just live with it, right? No matter what you do to compact, no matter what you do, water is going to ruin you, right? That's just one of the things. So this is just one example. This is a device that, basically I had a love-hate relationship with during my PhD. Throughout the 5 years of my PhD, I ran 216 shear strength tests on this one, and that was part of my dissertation and stuff like that. It was all assembled by hand and stuff. As you can see, it's not any vendor made. This was actually made by Professor Marshall Thompson long back, and this is one of the things. This is just my device from back then. But they actually developed something. This is another thing Professor Thompson developed. It's called University of Illinois Rapid Shear Strength, and there is a reason for that. When you are trying to do triaxial testing, if you go to typical geotechnical triaxial tests, the strain rates are extremely slow, right? If you're doing a drain test thing, you're really slow, right? And sometimes it can become prohibitively slow depending on what you're trying to get and stuff. So for rapid base and subgrade characterization, he actually came up with this method, which is 1.5 inch, which comes out to be 12.5% strain per second. A typical rate you will see is about 1% per minute. I'm talking about 12.5% per second. So this test literally takes 1.5 seconds to run once you assemble, right? But the good news is this is from some aggregate based materials. If a slow monotonic test 1% per minute, you got about 57.6 and 6.8. Here you are getting about 61.7 and 19.2. So very close in friction numbers and stuff. So for aggregates, when drainage is pretty much guaranteed, where excess pore water pressure and everything is not a problem, you can actually increase the shear strain rate and still get by with quite comfortably. And this helps a lot. Otherwise, the number of testing will actually be very limited for you. This is another very important thing for us to keep track when we go forward, and I'm going to show this to you in a couple of different ways. When there is a moving wheel load, right, So let's take a look at how a soil element feels it. This is the road, this is a soil element, and I am sitting at the soil element with a pressure sensor and my watch, or I just have a data acquisition system. So the truck is coming from somewhere here, this way. With time, right? This is time, this is sigma. With time, for some time it is 0, 0, 0, 0, 0. It starts feeling something. It goes and disappears, right? As that wheel moves. This is called a load pulse. That's called a load pulse. It has a definite duration, it has a definite magnitude, and as you can imagine, intuition says that what will happen if I plot for here? How will the pulse look? What will it look like? Shorter or taller? Taller. Wider or narrower? Narrower. So narrow but tall. You know that, right? So, but there is actually another thing that's happening here as well. In triaxial testing, we are always aligning the sample like this, and we are loading this way and confining this way and stuff. The problem is when the wheel is over here at one point, this thing is not just experiencing vertical load. It has components this way as well, right? So it has horizontal components, it has shear components. Triaxial testing, conventional, what is the magnitude of shear? That's why we do principal stress analysis and stuff like that, right? So this is how an actual element feels. So if you plot the stress pulses, you have a sigma V, the orange one, or yellow, or whatever that color is. Then you have the sigma H, right? And then you have a tau, and the tau of course is 0 when you are directly on top of it. That's the principal condition. But look at these points, folks, these regions. What does it represent? Horizontal is more than vertical. What does that mean? It's pushing this way more than it is pushing this way. So your sample is extending, which is not something that you are simulating in your traditional conventional thing, right? Let me draw one more thing for you so that so this is the chamber and this is the sample, and this is sigma H and this is sigma V, because sigma V has a deviator component as well, right? What is the relationship in here, mathematical relationship between sigma H and sigma D in terms of inequalities? In terms of inequalities, what always holds true here? Sigma V and sigma H. What should I write here? What is the inequality? There. Yes? Always. Can we simulate a case when sigma H is greater than sigma V in conventional triaxial testing? No. Right? But are we facing those situations? Right? So that's where we go into something called advanced triaxial testing. Again, something on Thursdays, maybe Wednesday afternoon or Thursday. I'll show you a setup, how that does, why it is important, wheel load simulation is important and stuff like that, right? So just a piece of trailer for you that this is something that's coming. So as the stress is coming, wheel is over here, right underneath. As it moves, the principal stress direction changes. It's not always vertical, right? The principal stress direction rotates under moving wheel load. So static simulation testing is very different from moving wheel load simulation and testing, right? So that's where permanent deformation and everything comes. Typical strength correlations, there are so many different strength values like CBR, there is beam stabilometer, there is DCP which we haven't gone into yet, there is Texas triaxial, there is unconfined compressive. People have developed empirical relations and stuff. Now how much you use it, again it all depends on what situation are you faced with, right? When my graduate student wants to do something for their thesis, I am going to say, no, go run these tests. But when an undergrad student working on a senior design or capstone design kind of a project wants some kind of information, I was like, okay, use this correlation, move on, because that's not your main focus. So you just have to realize what we are trying to do. Okay, so that's the base, like surface stuff of triaxial testing in terms of